Hi, welcome. This is the summary of chapter 1. Okay, it's a video summary. That doesn't mean that you don't have to go to the lecture room. You have to go to the lecture room. This is a summary to help your study. We will focus in the most important aspects of the chapter. Okay, chapter 1 is structure and bonding. We will talk about the atomic structure, the nucleus, atomic structure, the orbitals, the electron configuration, chemical bonding theory, chemical bonds, valence bond theory, sp3 hybrid orbitals and the structure of methane, sp3 hybrid orbitals and the structure of ethane, sp2 hybrid orbitals and the structure of ethylene, and sp hybrid orbitals and the structure of acetylene. Then we will focus in hybridization of nitrogen, oxygen, phosphorus and sulfur, describing chemical bonds, molecular orbital theory, graphing chemical structures, and finally a deeper look organic foods, risk versus benefit. Okay. Well, when we are talking about organic chemistry is very broad. We can have enzymes, we can have drugs. Okay, and the learning objective of this lecture will be, we will know how is the basic structure of an atom, the orbital shapes and the ground state electron configuration of atoms, the valence bond theory, what determines the length of a bond, energy minimization as a measure there in this course, should be able to say any energy is released when a bond is formed based on this. Bonding theory, specifically with orbital hybridization, sp3, sp2, sp, and geometries and bond angles of each. Orbital hybridization of atoms other than carbon, nitrogen, oxygen, phosphorus, and sulfur. Graphing chemical structures. What is organic chemistry? Okay, organic chemistry basically is the study of carbon compounds. Compounds that the major atom, the main atom, is carbon. Okay? For example, here we have, if we take animal fat, we make a hydrolysis with sodium hydroxide and water. What we get is soap plus glycerin. If we take the soap and we do another hydrolysis, what we get is fatty acids. Okay. If we take ammonium cyanide and we heat, what we get is urea. These are two typical reactions of organic chemistry, and normally organic chemistry is using the atoms that we saw here in color: hydrogen, carbon, nitrogen, oxygen, fluor, phosphor, sulfur, chloride, bromide, iodide. That means that we cannot use the other atoms. No. That means that these are the most often used. Okay. Take a look in the position of carbon. Okay, of all these compounds, of all these atoms, carbon is the less electronegative of all atoms, except hydrogen. Okay, hydrogen and carbon, we can say that has a more or less a similar electronegativity, but all the others, nitrogen, phosphorus, oxygen, sulfur, and the halogens are more electronegative of carbon, and these will determine his chemistry. Okay, then we take a look about the atomic structure, the nucleus. The atom basically is a small nucleus where we have protons and neutrons, and then a huge space where we have the orbitals, and is where are flying the electrons. Okay, nucleus are between 10 at minus 14 to 10 minus 15 meters in diameter, very small, and a diameter of a typical atom, as you can see, is by far higher. It's 2 per 10 at minus 10, at least 4 orders of magnitude more. Okay? That means clearly we have a very small nucleus and a huge free space where are the electrons. we have three different, as I said, we have three different types of structures in the nucleus, in the atoms. We have electrons. Electrons basically are negative, charge -1, mass more or less is equal to 0. Protons are positive, that means charge +1 and 1 molecular atomic mass. And neutrons are 0 charge and 1 molecular mass. That means if we want to know the weight of an atom, we have to sum protons and neutrons. If we want to know the electronic properties of the atom, what we have to check is the number of electrons or the number of protons. That has to be the same. Okay, we have the mass number, the element symbol, and the atomic number. The mass number is the sum of protons and neutrons. The atomic number is the number of protons or electrons, because it has to be the same in a normal atom. Okay, and the element symbol is basically the letter that we assign to the atom. For example, carbon is a C, hydrogen is a H. Okay, mass number is equal to number of protons plus number of neutrons, as I said. One important thing is that we can have several atoms that has different weight but are the same atom. Okay, what we cannot have is two atoms that are the same with different atomic number. This cannot be. However, the number of neutrons could vary from one to another. That means we can have a carbon with 6 neutrons, or we can have a carbon with 7 neutrons, for example. Okay, this didn't change in anything the electronic properties, because the electronic properties are determined by the protons and electrons, but will change the mass number. These atoms that has exactly the same atomic number but different mass number, we call it isotopes. Okay, then the electrons basically are included in an orbital. What is an orbital? An orbital basically is a mathematical expression, call it a wave equation, where describe where can be the electron. Okay, basically is like the probability to find the electron in some part of the space. The solution to a wave equation is called a wave function or orbital. That means orbitals basically is the part of the space where we have more than 95% of possibilities to find an electron. Okay? By plotting the square of the wave function in three-dimensional space, an orbital describes the volume of space around a nucleus that an electron is most likely to occupy. And we have these three electrons, these three orbitals, sorry. We can define s orbitals, p orbitals, and d orbitals. The s orbitals are a sphere, okay? P orbitals are like two lobules, one up and one down, while the d orbitals has more complex structures that we will not enter in this lecture. Okay? The two p orbitals can be oriented by each axis, x-axis, y-axis, and z-axis, but are the same. Basically, two lobules, two x, one one following one axis. Okay. Then, how the electrons are disposed in an atom? Well, the first that we have to define is the energy levels of electrons in each atom. Okay. The first energy level of atoms is the one shell, the first shell, okay, that only contains s orbital, an s orbital, one s orbital. That means the first level of energy of electrons, we only can put 2 electrons there. if we check the periodic table, will be the hydrogen and the helium. Okay? For the second level of energy, we have accessible the s orbitals, the 2s orbitals, I mean we can put 2 electrons in the 2s orbitals, plus the 2p orbitals. The 2p orbitals become accessible. And then we can put, because they are free p orbitals, we can put 6 electrons. That means that in the second row, in the second energy level, we can put 8 electrons. That means we can put 8 atoms. Finally, in the third row, in the third shell, we have access to s orbitals, 1, p orbitals, 3, and the orbitals that are 5. That means that we can put 10 more electrons. In total, we can put 2 electrons in the first row, 8 electrons in the second row, 18 electrons in the third row. And then we can talk about electron configurations. We can define 2 rules. One is the Aufbau principle, is related to the energy levels, where are the electrons. The energy levels are following the graphic below. Okay, here you can see the graphic. We start with the 1s, this is the minimum energy, then 2s, then 2p, 3s, 3p, but then instead to go to the 3d is going to the 4p. Okay, only this, I will not enter on this. It's like, it's for advanced course, this thing. But basically what we have is to follow here, follow this graphic to fill the orbitals. That means first 1s, then 2s, then 2p, then 3s, then 3p, then 4s. But we will never use an atom that is not in the first 3 rows or in the first 2 rows even. Okay? Then we have the Pauli exclusion principle. The Pauli exclusion principle states that 2 electrons cannot have the same quantum number. That means when we put the, here you have down, you can see the graphic, okay? We cannot put 2 atoms, 2 electrons that are exactly the same. For example, in 1s, if we put 1 atom with the arrow up, the next 1 electron with the arrow up, the next electron has to be with the arrow down. Because if we put 2 with the arrow up, we'll have the same numbers, the same quantum numbers, and this is forbidden. Okay, that means that we have complementary, 1 up, 1 down. In the 2s, exactly the same. In the 2p, we can have 3 up in different electrons, in different orbitals, and 3 down in different orbitals. Okay? As easy as this. Here you have an example of hydrogen, where we have 1 electron, we can put it up or down, the arrow, that's the same. And in the case of carbon, we have 2 electrons in 1s. Okay, we put the 2 electrons, 1 up, 1 down, in order to do the Pauli principle. Okay, and then 2s, 1 up, 1 down, and then 2p, we have 2 electrons remaining, and then we put the 2 electrons in the p orbitals. You can tell me why I put in this way. Well, then we have to follow the Hund's rule. The Hund's rule is that we have to maximize the total spin quantum number. That means if we have 2 electrons in 3 orbitals, we have to put the 2 electrons in the same direction, with the arrow in the same direction. That means that we have to put it in 2 different orbitals. If we have 3 electrons, we put 3 electrons in the 3 orbitals, as you can see in the case of phosphorus. Okay? However, when the people was checking organic compounds, they arrived to the conclusion that for a development of chemical bonding theory, the use of these orbitals was not so accurate. Why? Because they realized that the carbon is tetravalent. That means we have the carbon, and all the substituents of the carbon are in a tetrahedron. Okay, this was discovered by August Kekule. Carbon chains can double back on themselves to form ring of atoms, and Jacob Ganfos and Joseph Leville, 4 bonds of carbon are not oriented randomly but have a specific special direction. Carbon sits at the center of a regular tetrahedron. Here you can see. Okay, in the middle of the tetrahedron is the carbon, and then we have the 4 substituents. Obviously, if we have these bonds between the carbon and the other atoms that are around the carbon, in this case for hydrogens, the orbital theory that we did doesn't look very appropriate, because basically the first orbital is a sphere and the seconds are like x in each x-axis. That means doesn't look that the combination of these orbitals will give us a tetrahedron. Okay. Then we define the valence shell, the ionic bond, covalent bond, and molecule. Okay, the valence shell is the electrons that we have in the last shell. That will be the electrons that we will use for the bonding with other atoms. Ionic bond is when we have a bond that is totally broken. That means that one atom takes all the electrons of the bonds and remains negative, and the other atom doesn't take any electron and remains positive. Covalent bond is a bond where the 2 atoms share the electrons of the bond. Okay, and molecules is basically one of these structures that has covalent bonds. Here you can see different structures of methane, carbon bond hydrogen for ammonia, water, or methanol. Okay, and the electron dot structure. We can put the 2 dots of each electron, or we can put a line that represents a bond. Up to you. What is the valence bond theory? A covalent bond formed when 2 atoms approach each other closely and a singly occupied orbital on one atom overlaps with a single occupied orbital of the other atom. For example, here we have a hydrogen. A 1s orbital of the hydrogen is reacting with another 1s orbital of the hydrogen. Because they are hydrogens, both has 1 electron, they bond together and they form a sigma molecular orbital. Okay, we form a H2 molecule. Okay, and we say that this bond is a sigma bond. We will see in the future what means sigma bond. Okay, the bond strength is that when we form this, obviously we are having a stabilization where we have the sigma bond that is stable, and we have an anti-sigma bond that is unstable. Here you can see. If we check in the distance, of course, when the 2 atoms approach, we are forming a stable bond. However, if we approach too much the 2 atoms, obviously 2 atoms cannot survive in the same space, and then we will create a destabilization. That means that there are distance where the bond is more stable. Well, this in hydrogen is working very well, but what happens in carbon? In carbon we have s orbitals and p orbitals, and the first thing that we have to notice is that all the in a tetrahedral carbon, all the bonds are the same. Here you have the example. Okay, the Lewis structure, the molecular model, and the electron pair geometry. All the atoms around the carbon looks the same. Then the first thing that we need to do is to build the orbitals required to do the bonds. In order to do this, what we do is we join the orbitals of the shell balance, that are basically 2s, 2p, 2pz, and 2py, and we do a orbital hybridization. What means hybridization? We do a linear combination between all the orbitals. That we mix all the orbitals and we get an average. When we mix all the orbitals and we get an average, what we call it the average is a hybrid orbitals sp3. That means we join 1s and 3p orbitals, and what we get is a 4 sp3 hybrid orbitals. Okay, we join 4 orbitals, 1s, 3p, and we get 4 sp3. These sp3 are oriented in the tetrahedron. That means that the orientation of each orbital is in the right direction to form the new bond. In the case of ethane, what we have is the sp3 orbital of the one carbon, the sp3 orbital of the other carbon, with 1 electron each one, and then they join together to form the carbon-carbon bond. As you can see here, we form the carbon-carbon bond, and we generate the final molecule. Okay, what is the process? First, we make the hybridization of the orbitals between the s and the 3p orbitals of the carbon. We hybridize in order to get the 4 sp3 orbitals. In the case of ethane, we are using 3 of these sp3 orbitals, hybridized orbitals, to form a carbon-hydrogen bond, as you can see in the slide, and then with the remaining orbital we join with another sp3 orbital of another carbon, and we do the carbon-carbon bond. How we know an hybridization for an atom? Well, we only need to count the number of atoms bonded around the atom. For example, here we have ethylene, we have 1, 2, 3 atoms. If we have 3 atoms, we need 3 hybrid bonds. These hybrid bonds will be sp2 because they are only 3. In acetylene, we only have a hydrogen and a carbon bonded to the carbon. That means 2. This will be sp. And the rest of the orbitals, in the case of ethylene, the pz, and in the case of acetylene, the pz and py, will remain intact. Okay, we will only hybridize as much atoms as bonds we have in the carbon. Then, what is the structure? We know that the tetrahedron has around 109 degrees. Okay, this is the angle between two substituents in the tetrahedron. What is the angle in a case of sp2? In the case of a sp2 hybridization, all 3 bonds are in the same plane. For example, in the plane of the slide. Okay, and the degree between one and another is 120. That's easy. A circumference has 360. We divide between 3, 120. That means that the angle between the different substituents in a sp2 hybridization will be 120. What happens in the case of the sp? Well, in the case of sp, the angle will be 180. Here you can see the drawing with the hybridized orbitals, the hybridized sp orbitals, plus the pz and the py that remain intact. Okay, but here the angle between the two substituents will be 180. as you can see in all these drawings. In this case, we say that we have three different bonds because we have a sp-sp sigma bond, a pz-pz p bond, and a py-py p bond. Okay. Here is the strength of the CC and CH bonds in methane, ethane, and ethylene. As you can see here, in the case of methane, the carbon hydrogen is higher than not ethane or ethylene, and also the carbon-carbon bond in the case of ethane is higher, is lower than the ethylene and acetylene, obviously, because ethylene and acetylene is a double and a triple bond. But if we divide between 3 the ethylene and the acetylene bond, between 2 the ethylene and between 3 the acetylene, we see that the p orbitals are normally weaker than not the s orbitals, the sigma orbitals. Okay? Here you have the bond length. When stronger is the atom, that means if we have a single bond, the bond length will be higher. If we have a double bond, the two atoms will be a little bit closer, and if we have a triple bond, obviously the two atoms will be a little bit closer. What happens with the hybridization of nitrogen, oxygen, phosphorus, and sulfur? Well, exactly the same than with carbon. Okay, the only difference is that now we have a lone pair. In the case of the nitrogen, we have a lone pair. In the case of oxygen, we have 2 lone pairs, etc. Okay, here you have the methylamine. We have the free orbitals that we can do the hybridization, and we have a sp3 hybridization where a lone pair is occupying one sp3 orbital. Okay, and we do the same done with the carbon. The only difference is that because the pair of electrons are bigger and more electronegative than not a bond, the angle is a little bit higher or lower, depending on how you consider. Okay, that means the occupancy of the lone electrons is slightly higher. This is why we have a 107.1 degrees between the two hydrogens. Okay, or we have 108 in the case of methanol. Okay. Exactly the same with phosphorus. Here in the phosphorus, don't worry, phosphorus is from the group 3, is from the row number 3. That means that has accessible the d orbitals, can expand the octet. Remember that normal atoms like carbon or nitrogen will never expand the octet, only can have 4 bonds around, only can have 8 electrons around. In the case of phosphorus, they can expand the octet. Okay? But we will not enter in these lectures about phosphorus and this kind of stuff. The same than sulfur. Okay, basically now we will define sigma orbital and p orbitals. Remember that when we have a sp3 or sp2 we get a sigma orbital. When we are joining two p orbitals, that px, px, or py, py, or pz, pz, we get a p orbital. Why? Well, a sigma orbital is an orbital that along the line that bond the both atoms, they are not change or change of color or change of sign in the orbital. For example, in a sigma down, you can see that in all the carbon-carbon bond, up and down, we have the same color. Okay, this is a sigma orbital. However, when we are using a p orbital, up and down of the same line that bond the two carbons, we see that we have a different color or different sign. Okay, here you can see that up red, down blue. When this is happening, up red, down blue, this is a p orbital. When we have red red or blue blue, depending on how we draw it, we have a sigma orbital, as easy as this. How we draw the chemical structures? Well, the chemical structures are drawing using lines. Okay, each vertex of this structure is a carbon, and normally we don't draw the hydrogens. When we draw this structure, we know that in its vertex we have to add as many hydrogens to make the rule of the octet possible. That means, for example, in the first vertex of the skeletal structure here, we can have 3 hydrogens, in the second 2 hydrogens, in the third 1 hydrogen. Okay? Here you have different skeletal structures. Okay, we can put the hydrogen, we cannot put the hydrogen, it's up to you. Normally when we go to advanced organic chemistry, we never put the hydrogens, okay? And when we have a double bond, simple, we put a double dash, and this indicates that we have a double bond. Okay, and that's all. Thank you very much for your attention. I hope that this helps you in your study, and see you in the next lesson.